Okay, the last thing I wanted to do to wrap this up is to summarize the parameters. I'll also put these in the latest version of the mini project, but if you look at this video, you'll find the parameters you should use. So getting these parameters in is the first critical step. The next part, getting your variables inputted. So we have our stress, our strain, plastic strain. Here's your total strain. Here are the parameters associated with the dislocation of force balance. Here's the applied stress. Here is the slip direction, slip plane. Here is the applied shear on a plane that gets activated anytime this applied shear is greater than the yield, or it's less than the negative. So otherwise, if your applied shear is less than the critical amount, or the magnitude of this is less than that critical amount, it'll be purely elastic and there will be no dislocations. Next key part, you need to put in the equations for plane elasticity. This is the PDE, the boundary conditions, and the dislocation model. So all those were described in the previous models. Now, one thing that I've done, I've gone back, I'm using a fine mesh, which we found to be reasonable, and then the results. So I'm summarizing a lot of results at different angles here. So these were a few things done in class, and what we find is, so these are simulations at different slip orientations. So if I come back up to parameters, this angle here, so I varied this angle and rerun the model, and you got the following results. So if we plot this, here's what we see. And if you looked at previous simulations, we were seeing this overshoot and then it would stabilize. The main thing I changed was the dissipation. This is a viscous coefficient that smooths this out, so this looks more like a diffusive type problem. So let me go back to here. So this is the final result that you're really after. So you want to go in and look at what angle generated this plot. So this is a measure of the plasticity that occurred in the material. So you want to label what angle this is associated with, and then you can say, okay, at so-and-so angle, this was the maximum amount of plasticity for a circular hole. Note now, this is an elliptical hole. The result may be different if it's circular. So to finalize it, I will run this so you'll get an idea on how long it takes to run. It should only take probably less than a minute to run. So so here it's loading. Let's see if we can zoom in while it's simulating. So yeah, right here is where you see now it's starting to go plastic. This is going to grow some. So it's taking a little while. This is up to 0.3 seconds. But it's propagating along fairly quickly, so this should only last another less than a minute, I would say. So what I'm plotting here, you'll see right here, it's the absolute value of the gradient of gamma in the x as well as in the y, gradient in the y. That's what so to summarize, when you turn this in, I would include a plot of this at some respective angle, and then the other plot showing the plasticity that occurs over time, that integration over the total area. So include that and clearly show which angle you get the maximum amount of plasticity. So I think I'm going to kill this right here. You can see it's moving along fairly well. It may take another 30 seconds or so, but for a circular hole, you should start seeing some type of plasticity in this range. You may get some here, I'm not sure, but most likely you're going to get the most of it right there. Alright, so that concludes this tutorial on dislocation mechanics.